we're very happy to have Keshav from UAC. Could you be telling us about letting the public history of this?
Hi, yeah, thanks for the introduction. So I'm Keshav Kapoor. I'm a PhD student at U of I, and my advisors are Paul Kwiat and Virginia Lorenz. So today I'd like to, as Piyush mentioned, talk about this first node of a public quantum network we've created in the Urbana-Champaign area in partnership with a public library there, the Urbana Free Library, as well as UC2B, which is a fiber broadband not-for-profit. So just to give an idea of where we are located. So in the United States, we're in Illinois, which is in the Midwest, the central US. And more specifically, within the US, we're here, and you might know Chicago. We're relative to Chicago, we're about 120 miles south of Chicago, about a 2-hour drive south of Chicago. And this is a map of UC2B's fiber infrastructure in Urbana-Champaign, as well as this smaller town that's also connected called Savoy. So what we're aiming to do in Urbana-Champaign is make a citywide quantum network, citywide scale quantum networks, but with the caveat that we want to make them publicly accessible from the onset. And beyond the publicly accessible part, we still want to use these quantum networks for fundamental research and do actual experimental quantum violations of classical bounds on
publicly accessible is the public in Urbana-Champaign or public everywhere?
So right now it is just Urbana-Champaign. The way you can access this network is by going to Urbana Free Library. We see ways to make it accessible beyond that, right? People can just go online to some website and do the measurement. But right now it's just they have to go to the library. Okay, so just what a quantum network is, before I delve too deep into it, is it's so in a classical fiber network these days, information is transmitted using photons still. It's still light, laser light, but it's relatively high power laser light, so it behaves classically. But still the same way, information is basically transferred through light pulses and signals. But in our quantum internet or quantum network, we move towards a less intense light. We move towards single photon level signals, where we distribute, for example, we would distribute entanglement between 2 photons, which we would send through these optical fibers. So that's an important point to note, is that we can use the existing broadband infrastructure that's already created, these telecom classical networks, which are already created. Our quantum level photons will simply travel through the fiber in the same way, although we are more susceptible to loss because quantum principles, the no cloning theorem, means we can't basically amplify the signal like we would with a classical internet signal. So there are some limitations we have by sending quantum signals through here, but we can use existing infrastructure. Okay, so what would we actually use this quantum network for? So one of the first applications that came out was this quantum secure communication, such as quantum key distribution, QKD. This came out because of some algorithms which were created, which could basically break modern day RSA encryption. But those algorithms are quantum algorithms. So there were quantum algorithms which could factor large numbers. And so to sort of counteract that, in preparation for a quantum computer to be made, people came up with these QKD protocols.
Wait, that's factoring, right?
Yeah. We can also use it for more scientific purposes, like quantum teleportation. So quantum teleportation is basically transferring the state of one quantum particle to another quantum particle via a intermediary quantum particle. So it's a 3-particle process. And so this quantum teleportation has actually been shown already. But yeah, so this quantum teleportation is still necessary to do make wide-scale networks, for example, because again, like we can't amplify the signal, so we can use quantum teleportation to sort of extend the range on which our quantum signal can extend.
Why is this teleportation not transportation?
That is, I think just what they called it. Or it's the idea. So yeah, so the idea though is that you have one particle here and the other particle here, and what you're doing is you're transferring the information without actually transferring the particle from here to here. So you're sort of teleporting that information without having an interaction,
There's a third particle.
Yeah, so there's a third part. So it starts out with, so let's say this is the particle you want to teleport to. You want the information to be teleported to this particle. So this is, you start with an entangled state between these two particles. Then you take the particle you want teleported and you interfere it with this particle. And so this particle never has to interact with the first particle.
I see.
And you get the information across.
So it's via that.
Yeah, exactly. So with this, we can sort of make this quantum internet. And this uses, I mean, there's many other infrastructure that still needs to be built out to fully realize a actual quantum internet. We need things such as quantum memories. But the idea at the end is using sort of a combination of both free space and fiber optic network links. We'd be able to transfer information, quantum information, which we can use to, for example, with quantum computers, once we have quantum computers, good enough quantum computers that are linked with these photonic network interfaces, we could, for example, do distributed quantum computing. And of course, one of the reasons we made this public is there are probably many unforeseen applications of quantum networks, which as researchers, we are unable to see. And that brings me to this point, right, where we're making this public quantum network. So what you see here actually is a flyer we distributed for our launch event back in November of 2023. What we're doing here is actually allowing the public to, in real life, interact with quantum photons, which are sending through the network in the city. And we really want this extensive public engagement of our system. So this first part, which we realized is this hands-on public participation. So that's kind of where we started with, right? Is we have this quantum network, and people can go and actually do measurements in real life on these entangled photons, which we're sending through our network. And to that extent, we've actually had multiple field trips since this launch event. So people, like school children, come and we actually take them to the library and show them how to use the quantum network and all of that. And we also actually, if it's a field trip, we usually bring them into our labs and show kind of the behind the scenes of what's going on as well. And to this extent, we also want to be working with other educators, people in both school grade K through 12 educators, as well as the community college system in Illinois to develop quantum curricula, to develop a quantum aware workforce. But beyond this, we still want to do fundamental research on this network. We are researchers after all. We don't want to just create a network and not do anything new on it. So we haven't realized any of these tests yet. We've been more focused on creating just a network and actually having a robust infrastructure for public participation on it. But we are in the plans to do some of these more state-of-the-art quantum protocols as well as fundamental tests.
So the difference between a classical network and a quantum network is that classical network it sends a lot of photons because everyone by one.
You could, I mean, at the very basic level, yes, right, is at least the networks we're using right now, which rely on the existing telecommunications hardware, yes, we are sending photons at the single photon level and then the information is also inputted differently at that point, right? Because so the way we're encoding information is with the polarization of the photon. I'm not quite sure all the ways which they encode classical information, but it's like you could have it with the intensity, right? For example, of light coming through, but you can't really encode intensity for quantum information. So there are some more differences.
So what I wanted to know is how much energy does it save?
Energy. So let's see the energy of one photon, right? So we're
suppose I want to send a 10 petabytes file over to you, and I send it using classical system. How much energy would be saved?
I don't think that much energy would be saved because, for example, this QKD system, right? You can think of that as transferring information between two parties. This is like any realization of this right now is like bits per second. So you would, and if you really want to look at the energy, which there's quite a bit of energy required to, at this point, to create those single photons, right? We use, I'll come to this later when we talk on how we actually create those photons, but that in itself right now is a very efficient process.
So it's harder to create.
Yeah. So I would actually suspect at the current infrastructure we have on this, I would suspect we actually would spend more energy transferring that information from classical.
Point that UPD works, that your basic cryptography is based on physical law rather than other.
Okay. But what do you mean if UPD works? You if it can be.
Works very practical. It works very only law.
I see.
We just have to believe that
So I think one of the concerns often with building quantum machines or something is to somehow deal with the decoherence.
Yeah.
So is that
yeah, great question, right? So this is the nice part about working with photons. They don't really interact with the environment. So we don't have to worry too much about decoherence with photons. There are some other things which happen in the fiber, such as, for example, if we encode in polarization, it'll actually do a transformation on the photons going through. But this decoherence isn't really something we worry about with photons. It's more loss in the optical fiber as well as the polarization transformation.
So this makes sense. So once you send the entanglement folder to some other fiber network, so you have to kind of capture it to get the benefit, right? So that you can send information. So that you can teleport information.
Sure, you have to detect it. You have to do some measurement at each end to get.
Yes, so I mean, but you have to do this if the photon doesn't live for too long, and not able to capture it for long enough, then there is no benefit to get.
Yeah, so right now we don't really worry about preserving it, right? Like I think what you're getting at is like a quantum memory, right? You send it over and then you capture it in a quantum memory and have it stay there to do operations, right? So right now in our current implementation, we aren't capturing it in a quantum memory, we're simply doing a measurement on it. So the photon comes there and we do a measurement and then we post-process information.
So right now we see this as a class. We just as a class.
Yeah, so when we need to verify that, so what we're doing is a CHSH inequality test, which is essentially just verifying that we have entanglement between the two. To actually verify that, yes, we need classical communications and we're only as fast as those classical communications.
if the then you get concentrated speed limit.
So what, maybe we can discuss this more, but I'm not sure exactly what the speed. So yeah, but we are sending that classical communication over a completely separate channel. But yes, we are communicating classically for the CHSH test. Yeah. What the people at the library see?
Yeah.
That's later in my, we'll get to that. Okay.
So what is the sort of bit rate that you get? Like how many photons can you send per second?
Yeah, so I'll get detailed.
Okay.
So, yeah. Right. So again, this is kind of the inception of the idea, right? Was that when phones first came out, people had no idea. Yeah, I think this is pretty similar to one of the Alexander Graham Bell's first devices, right?
Okay.
And then eventually we got cell phones, and then there was like this famous Nokia phone, indestructible Nokia phone, but we really didn't get all that many public, like around here we started getting like public ideas of what to do on this, right? People would send ringtones and stuff on this, but by the time we got to the iPhone, now people have no idea what's going on inside of the iPhone, but they're still able to create applications to do with it, right? They have like the app development is massive now. And so this is kind of also one of the reasons why we developed this publicly is right now we're sort of around here in our development of these quantum networks, but we're hoping that introducing this quantum network to the public this early will actually like make them quantum aware, and they can at least have some idea in mind of applications that can be made on basically each stage of this process. But we're definitely on this side. Like right now, we in the lab we go and we are actually like doing the switching ourselves right now. So we're very early stage, but we want to make sure that people are quantum aware as we develop these new systems. So this is sort of the timeline of the things that happened for where we are right now with the network. Though there is one important part is that in fall to winter of 2022, the Nobel Prize in Physics was awarded to Alan Espay, John Clauser, and Anton Zeilinger for actually doing these CHSH measurements to measure that entanglement was real. So before coming back to this, I'll just go a little bit into the CHSH measurement itself. Not too deep, just to give an idea of what's going on. So there's this like Einstein, Podolsky, Rosen paper, right? They're very hesitant to believe that entanglement actually exists in the third. They think there's some other like local hidden variable that's actually doing all of this entanglement that it hasn't been captured in the quantum theory. It took a while, but in the 60s, the scientist John Bell, he came up with Bell tests. So this was like the first like formal way that you could sort of show whether entanglement actually exists or if there are these local hidden variables. But this wasn't experimentally realizable, his formulation. So in the 70s, this is when that CHSH inequality came about, Clauser or Shimoni hold. And this was actually experimentally realizable. And I'll get to how you actually do this. But in the 70s, they actually did these measurements, and they were actually fully expecting these like local hidden variables to be real. But to their surprise, they actually proved that entanglement was real. Then it took a while, but like 50 years later, they got the Nobel Prize for doing these experiments. And then because these experiments, which were sort of we could do on our network, and there was quite a bit of publicity with this Nobel Prize for it. We decided to use the CHSH experiment on our public quantum network. This is what the public would actually come to do, is a CHSH experiment with the tagline that you could actually come and, like in real life, do an experiment that won the Nobel Prize. Right, so I could skip over this slide if you guys already know what entanglement is. Okay. So the idea of entanglement, at least mathematically, is that you can't separate, you have to have at least two quantum particles. And the idea is that you can't separate them out. So if you're able, so this like tensor product is how you sort of separate them out, right? And this first state that's written, right, this 1/2, 0, 0, 1, 0, 0, 1, 1, 1, where this first indice is the first particle and the second indice is the second particle. If you're able to separate them out, then that means that they're not actually entangled, which you're able to do in this case, right? It's pretty easy to see that you can write it as a tensor product of this superposition of the 0 and 1 state, again with the 0 and 1 state, right? So this is not entangled. However, if we look at this second state written here, this 1, 0 plus 0, 1, now, no matter how hard you think about it, right, there's no way you can separate these out into this first state tensor product into the second particle state. So that is more like a mathematical idea of entanglement. But thinking about it more intuitively, it's this idea that once you measure this first one, you know the state of the second one, right? In this first item written here, right, this first state written here, let's say I measured the first particle, and the first particle is in the ground state, the 0 state. You still don't know what the second particle is in, right? It could be in the 0 state or the 1 state still.
This thing by itself, this is like classical world.
Yeah.
We have classical problems because cannot be a product state before one, you know the other.
Yes.
It's there are certain actions you can do on it.
But there are differences. So in probability spaces, I think it's the other one. And here the way it's written is the other two.
No, but that's probably just but it's just that there are operations you can do on
Transform them.
you can transform them very differently that you can't do.
That doesn't come out.
Yeah. Okay.
I mean, and similar to that, right, is we have this Hilbert space, which is sort of how the quantum state spans, right? You have two particles, you have the 2 to the n Hilbert space, but then you're only looking at a subset of that for the actual entangled states that are possible. You sort of cut it out. So this is our basic introduction to what a Bell test is. So this is classical, right? This is the classical state case. Let's consider we have these following 4 statements, and let's work through them, right? So it starts out by saying A0 is equal to B0. Okay, so then it says A1 is equal to B0, which just by classical mathematics, transitive property, you can say A1 is equal to A0. Then it also says A0 is equal to B1. So that means B1 is equal to B0 as well as B1 is equal to A1, right? Everything's equal. But then this fourth statement, A1 doesn't equal B1, this cannot be true now, right? So it's sort of these contradictions in these statements, right? Which we can, again, this isn't the actual Bell test, but this is sort of a start to think about it, right? Is that now if we add the number of true statements we see here and subtract the number of false statements, we're bound by this 2 value, which also happens in the CHSH and qualities and Bell tests, is that we have to break this 2 bound. If it's below 2, we haven't proved that the 2 particles are entangled. If it's above 2, that proves that the 2 particles are entangled. Okay, so then we move to the actual quantum case, right? So let's say we have 2 particles here. These can be photons, whatever, 2 entangled quantum particles. In our case, we use photons, which are entangled in polarization. So we can ask this first one what polarization is in, right? We can ask it horizontal, vertical, diagonal, anti-diagonal polarization, as well as circular polarizations of light. We have many options of these sort of questions to ask that particle. And if you go through the CHSH inequality, there is sort of, if you ask this particle a question, what is the best question to ask this other particle to maximize your violation? But the basic idea, right, is that every time we ask whether this is vertically polarized, we will see that this is also vertically polarized. And it doesn't matter how far apart they're separated, we will always see these correlations. And the other way as well, if we measure this is horizontal, this will be horizontal. So I mean, the actual photons we use, which I will get into much more detail on, are actually anti-correlated. So this horizontal would mean this is vertical, but we can do the same Bell test on that state. So yeah, this is the basic idea now, is that this two value sort of separates out our cases where we cannot prove that the two particles are quantum mechanically entangled with each other versus above two where they are quantum mechanically entangled with each other. Again, this slide is directly from the presentation which Professor Squiat and Lorenz gave when we first launched at the launch event on the before. So this is kind of how we were trying to get to the public, you know, like this meter, is it above 2 or below 2?
I don't understand this.
Yeah.
So when you say you can have some number, true minus number of false with quantum, how is that?
Yeah, so we see, good question is that we see, so basically.
No, so wait, so
Yeah.
this state more clearly, what is the A0, B0, what are those?
Yeah, so the A0, B0 are actually these like expectation values. So we measure the polarization of a photon in a particular basis of polarization, as well as this one. The second one we measure in a same or slightly different basis, and then we see the amount of correlation between the two. So these turn out to actually, instead of being like 1 or 0, like right, this is like a probability 1 or a probability 0. They have some probabilities assigned, right? So these next ones, we basically have the probability state of this being in the horizontal and this being in the horizontal. The probability of that happening, or the probability of this being in the horizontal and the probability of this being in the diagonal. And those probabilities added up to each other if these were classically correlated, or if they weren't entangled. Those added up probabilities would be less than 2. But if they are entangled, then we see this weird behavior where those probabilities end up being greater than 2. And there's the actual like choice of those basis angles I haven't gone through, but that was shown in that first CHSH paper.
So this is the beta version of CHSH?
No, the actual measurement we're doing is the full CHSH.
No, but this example.
Yeah. This is not the full CHSH. Yeah.
So here, should I think of it as saying there are two particles A and B, and A0 is maybe, I don't know, the number of, I don't know, some event when you saw particle A in state 0.
So
is that what I should be interpreting?
I don't. Yeah, you can. So I think it's not too important here. The important part is A0 and B0 are two different. And I guess the way you would sort of get them to the quantum case is that these would be sort of two different measurements on the system, like the probability of this happening where A0 and B0 are the same. Yeah, so this, I think, I don't think, right, if we could have a direct classical to quantum sort of link here, then we won't really see the quantum behavior.
One very recent test, the recent particle, someone produced two measurements, and this measurement had 2 reports. And now different probabilities of getting. If this thing was the model of the world was that there is somebody was sampled from and then you see whatever when you look at it. There's this in the sense that the correlation you can see that any okay. probably arbitrary.
But there is an example of an entire quantum simulation where you can exceed.
Yeah, the model is not like a monopoly. Okay. Okay. Therefore, the solution is legal right.
This is the extra bit that what is the difference between the entire space?
Yes, the model is not a correlated in sample in the deep. It has to be something different. Because in that, any one of that, right?
Yeah.
The answer will never be no. Because everything is okay.
The point is, in classical correlation, there's only one kind of measurement, right? And we have this quantum so-called entanglement. The fact that you can change the basis of measuring different.
Yes, that is going to be
But that's an essential thing. You did in the same way, basis, even with classical correlation,
A measurement could be an event.
yes,
Yes, so you're conditioning on an event. That's like an, you could think of that as.
so all it is saying is that
this linear change of basis is a very different kind of.
yeah, it is a very, and all it is saying, the policy something and some of the single point that your model of the world cannot be described by a
Yeah.
whatever person that someone sampled it and then get the result and when you will just see what that will never explain it.
That's probably because
Of this
this is and this is what actually prevents the assumption that there is a I can fix my rent.
yeah. So
That doesn't
Yeah.
happen with this linear. That's
Yeah,
what I
yeah.
mean.
Yeah.
That doesn't happen with this linear.
No, right, so yeah, the board part here is that you have to choose, there's like a very specific basis of measurement,
Yeah,
right?
so there's no
Getting the violation. Which is, yeah, so exactly, there's like you see that you don't get a violation depending on what bases you measure the two particles in. There's a specific basis one you reach that you actually start seeing this violation. I'll show that later again because that's kind of what we want the public to do as well. Yeah, so just again, so Professor Lorenz actually had the idea for this before I joined the PhD program in 2022. And then once I got there, the first thing we did was actually the polarization and loss characterization of our fiber link. Then with the idea that we wanted to do the CHSH inequality, we started our source development as well as developing the public interface. Summer of 2023 is when we actually really started developing this public launch event and how to explain this entanglement concept to the general public. And then we actually had the launch event in fall 2023. And as of summer 2024, we have the current version of the network with what we call a fully automated measurement, which again, I'll get to towards the end of my slides. So before I continue too much, I'll just briefly tell you about our partners in this. In addition to U of I, we have Urbana-Champaign Broadband, which is a not-for-profit, which provides basically broadband networking to underserved communities in the area that was federally funded. And this is a partnership between the university and the cities of Urbana-Champaign. And the basic idea is that it links together most of the public institutions in the community. And what they've done for us is they've donated two fiber strands, which we have full control over for this project, as well as providing support and service for those fibers.
These fibers are off-the-shelf fibers.
Yeah. These are just the standard fibers they use to connect the rest of the community. These are the Corning SMH28 fibers. Yeah.
Sorry.
Yeah.
When you say they donated two fibers, these are two strands in the existing network in the US.
I don't quite remember if they were existing prior. They might have actually pulled the fiber through for us, but this isn't anything that goes too much above what they already do. Right? This is what they do. This UC2B basically makes fiber infrastructure and provides some networking for public institutions. The second partner is the Urbana Free Library. I believe this is actually one of the first public libraries in the US. It was founded in 1874. So it's like 150 years old now. And before everyone had like smartphones and stuff, they were providing free internet service for the community as well. And they have many computers there. People can go there, get on the computers, go surf the internet, all of that. But this is slightly more in line with what we do. They're quite involved in the community, and especially for STEM. So this Teen Open Lab, which is sort of like a STEM focused workshop for teens. They run and they've been running since 2013. And this, this happens multiple times a month, and they're basically guided through some STEM focused activity for a couple hours in the afternoon after school. All right. So again, this is just to give some idea of the physical layout. So we are here in the Loomis Lab of Physics on the University of Illinois campus, and this is the Urbana Free Library. So just to give an idea of kind of how the town is laid out. So both sides are on the Urbana side of town. This is the library. Yeah, this building is the library. This is the lab. This is Loomis Lab on the U of I campus. So this street here sort of separates the campus from the rest of the community. So this is the actual town of Urbana, and this is the campus. This is one of the major streets on campus, Green Street. So basically we're here, and just about a mile down the street, we have the Urbana Free Library. So the actual road distance between the two of us is only like 1.5 kilometers. We have, again, and then our fiber loop goes from Loomis to the library and back to Loomis. This is a 3-kilometer road trip becomes a over a 24-kilometer fiber trip for us. And this is mainly, we believe, due to how the fiber is routed on the University of Illinois network. And the IT department doesn't tell us how they route it. They think it's a security concern. So all we know is that there's a lot of fiber before we link into the UC2B part of the network. We measured about a 10 decibel loss at 1550 nanometers, which is where we operate. We did this measure. We do have an OTDR for this, which obviously gives us a slightly less loss value, but yeah, so we see about a 10 decibel loss. And this is slightly more important to us, is this dark count rate. So this is the rate at which we detect photons on our detectors without us sending any signal through the fibers. So we see that there's like this base count rate of 1500 just by linking our detectors into the fiber. This is some spurious signal. We suspect we don't have any like false detector counts. That's very low, maybe 100 or so, or under 100. The way our detectors are calibrated, might be like light leaking in from neighboring fibers, or when it goes out into the network closet at the library, some ambient light coupling into the fiber. So the polarization stability. So for this link, we see that the polarization angle or difference is maybe about 10 to 20 degrees change over the course of this measurement, which was 16 hours. So it's not too much for us. And what we really care about is this depolarization, which basically shows how different the polarization of this 1550 and 1549 state is, nanometer wavelength of light state is. So we have seen fibers where the difference between the polarization of this 1550 and this 1549 is much larger. And in that case, that's what we consider our depolarization or dephasing. But for this case, it isn't that much. And there are ways to fix this dephasing, which we are looking into. Yeah.
So can you just elaborate how this measurement is made?
Yeah, so we actually do this in 2 ways. I don't think I put the slides for this in the supplementals either, but essentially we start with a very narrow line width CW laser, so like 10 kilohertz line width. We ensure that it's well polarized, and then we send it through the fiber. And then we actually have two separate measurement devices at the end. So we measure this with a off-the-shelf Thorlabs polarimeter. Just measure the polarization over time while varying the wavelength. And then we have our own house-built polarization analyzer with some algorithm which reconstructs the polarization.
So this is constantly sending one particular polarization for all these hours,
Yeah,
correct?
yeah.
And you ensure that this polarization remain exactly what it
Yeah,
was.
we put it through like a polarizer.
Okay,
yeah.
so that will not change.
Yeah.
But over on this side is the fiber which is seeing the change in the environment over several hours.
Yes. Yeah. So it's less noticeable for this, but actually we have another fiber link which is longer and passes by a major interstate highway in the US. And there we actually notice right around like 5 and then early in the morning, we see a lot of polarization change, likely due to traffic on that highway. So this is sort of our vision for this. So we have a polarization entangled photon pair source here. So we'll have two photons that are entangled with each other. We send them through the fiber. The one we keep in the lab, we measure in the lab, right? So it becomes some definite polarization state after we measure it. Someone will come to the library. They'll tell what polarization settings they want to measure. And so there's some communication that happens back to the lab and then the network closet. We separated out the public station and the network closet because we have actual optical equipment here, which we don't want to get misaligned and such. But based off of their settings, this also does some measurement. It projects the polarization state, and then both photons come back to our detectors, these superconducting 9-wire single photon detectors. These are very efficient. They have like above 90% detection efficiency. And then we do basically correlation measurements between these two at multiple different settings of the polarization measurement to get our CHSH inequality. So it's important to note that here we don't do any active polarization correction. We do passive manual polarization correction because these CHSH measurements take on the order of minutes. So we don't have to actively correct for this polarization drift that's happening. And I'll show how exactly that affects the CHSH later.
This experiment again. Sorry.
Yeah.
This experiment
Yeah.
So what you are now trying to improve upon them is, am I right in understanding that you can, how far can you entangle photons?
So I wouldn't. So the purpose of this mainly is to introduce this concept to the public. I wouldn't say necessarily in this specific experiment we are improving upon any CHSH measurement that's been done in the past.
It's just a demonstration.
Yeah, it's a demonstration for the public, but it also because we have to make all this infrastructure to actually get this to the public, we can now use this network to do other more fundamental tests.
Oh.
Yeah. So there is that idea of how.
So the infrastructure.
Yeah, yeah, we do have ideas of how to use it, but this in itself to make this infrastructure took like 2 years to do. Yeah, and again, we can discuss this. I'll discuss this very slightly in my end slides, but what we're actually doing on longer distance scales. This. Okay, so now I'll talk about our entanglement source itself. This one is located in our physics lab on the U of I campus. So here is the actual, this is like a picture of our actual source. This is the source that's being used for the network. And we use this thing called spontaneous parametric down conversion, which I will actually explain a little bit in the upcoming slide because of I need the audience. So here is actually that crystal, that SPDC crystal. It's a little hard to see, but between this black part and this gold part, there's this 3 centimeter long crystal. And this is actually where that entanglement is generated. Okay, So just some brief overview of SPDC, the spontaneous parametric down conversion. It occurs due to second order nonlinearities in electric fields in some crystal medium. So here is a Feynman diagram of what's happening. Basically, one high energy photon gets split into two lower energy photons, which are entangled with each other in polarization. So what we have here, right, is this idea that you have this W3 is a pump photon. So this pump photon carries some energy, and then with some low probability, some like very low, like I believe on the order of 10 to the minus 5, 10 to the minus 6 probability, you produce two daughter photons from that initial pump photon. And the properties of these daughter photons is that the energy of these two has to sum up to the energy of the initial pump photon. That being said, they do not have to be the same energy, right? They can be different energies. When they're the same energies, we call that the degenerate case. The other property is momentum matching. So if the pump has this momentum, then the momentum of the two daughter photons, this K2 and K1, has to sum up to the momentum of the pump photon K3. So this is sort of one of the ways you create this entanglement. So you have this BBO crystal. So there are actually three types of crystals that with different like entangled polarization properties of the daughter photons relative to the pump photon. We use type 2. So what that means is that we call the pump axis the extraordinary axis, and the axis orthogonal to it the ordinary axis. So for a pump on the extraordinary axis, we create one photon on the extraordinary axis and one photon on the ordinary polarization axis. And what we see here, right, is this another type 2 crystal. You produce the extraordinary axis of one set of photons here. That's that K vector, that momentum. And the second one, momentum vector, makes it point out slightly below it. And if you see spatially, right, where they intersect, then you cannot tell until you measure which of those two photons you actually have. So that's where you create this entangled state of HV plus VH. So how do we do it? Again.
Oh.
Okay, yeah. Okay. So we use what we call a Sagnac interferometer setup, which I will walk through how we do it. But we start out with this 1560 nanometer pulsed laser. So our two daughter photons are, so it's a degenerate case, our two daughter photons end up at 1560 nanometers because we start out with this 1560 nanometer laser, we get to a second harmonic generation stage, which makes that 1560 like 780 nanometers. So from there, we do some polarization cleanup. We make sure it's basically diagonal polarization. So once we have diagonally polarized light, which is half horizontal, half vertical, we send it to this polarizing beam splitter, which creates our Sagnac interferometer. And there it splits up into its horizontal and vertical components. So the horizontal component passes through. So yes, the entanglement is created in some combination between this crystal and this polarizing beam splitter. Right now, where I'm in the explanation, that entanglement hasn't been created yet. But yes, at this beam splitter is where that entanglement is really created. So because the crystal only has one extraordinary axis, we have to make this photon horizontally polarized to match the extraordinary axis of the crystal. We then because this PBS, it's not a 50-50 PBS, it separates it based off of its polarization. So we want 50% of the light to come here, and 50% of the light to come here, because it's polarizing, we need it to be diagonal to get 50-50. So then we make it horizontal again, we get to the crystal, and here occasionally we get both processes creating a pair of entangled photons. And then these entangled photons go back through the interferometer, they reach here, right? And so what happens is that one of these entangled photons is horizontal and the other one's vertical for the direction going this way. And then alternatively, for the photon traveling the other way in the interferometer, we also get horizontal and vertical. Though it's changed slightly because of the half wave plate, we get vertical and horizontal. And then when they reach back at this beam splitter, because they're supposed to be spatially overlapped when they reach the beam splitter, then the horizontal of this clockwise direction passes through this way in the idler arm, what we're calling the idler arm. And then the vertical of the anti-clockwise process also passes over the idler arm, and vice versa for the signal arm. So at the end of the day, we basically have one photon from each process in each arm. And we create this HV plus VH state, which for the initial test of our source, we project, do the projection measurement in the lab and measure at our SNSVDs and do the correlation measurements. Yeah.
So this process, not all the lines that you see there entangled photons, right? But
Yeah.
it's like everything that goes to the process. And
No, so
sometimes it will entangled photons and sometimes it
it's so I will get to that again, but it's the idea of how efficient your process is. For us, this process is currently not very efficient for us.
lines and red lines are really so is it done in air?
No, this is done in air. So these straight lines you see, this blue and red and orange straight lines you see are in air. These yellow sort of squiggly lines you see are the fiber, as well as this green line here.
Okay, and just to be fair, so the PPKTP crystal that you have.
Yeah.
So the eventual thing is at some point you want to make sure that that crystal receives, I don't know, a high energy photon in a certain polarization.
Yeah.
And then there's something in it that might spontaneously produce two entangled photons out of them. But this is not always the case.
Yes. Yeah.
But it's like one in a million.
Yeah.
And the mechanism also filters out and only retains the 1 in a million thing that happens, or it's just that the other ones just become some noise in the final.
See, so the idea is that by and large, the only 15, 16 nanometer photons you see are produced by that process.
Oh,
so that 780 nanometer light, which is the pump light, we filter out. So we're only looking at the 60 nanometer light. But the actual efficiency of this entanglement generation between these two processes, we see in our system is in 2. Yes.
When the photon travels to that blue thing, enters the red part.
Yeah.
And then it reaches PDS.
Yeah.
Thereafter, you show like there were 2 dots, right?
Yeah.
Does that mean like actually there's what I mean, it's progressively either going to this or that or?
So maybe
So could I view this as a like after it first crossed the PDS? Could I view this as I mean, it's being shown in the picture as something that's like one photon.
yeah.
In the superposed state.
Yeah.
Some of it is going there, some of it is coming down. Right?
Well, there are
Some
two.
probability.
There are 2 photons.
So you have say 1 million photons something.
Yeah. Yeah, exactly. Like, I mean, but it's not like one, the first time it goes to the PDS, it's not like the photon itself gives rise to 2 photons, right? That
No.
only happened at PPKT.
Yes. Yeah. Exactly. So this is what we call a probabilistic
Right. So
source.
it's like, I mean, the fact that you're showing 2 lines there is like, with some probability it goes there and with some probability.
No, there are 2 photons, and so every time we measure a photon here, ideally we should have a corresponding photon in this arm.
No, that's after you went through the
Yeah.
PDS, right?
Yeah.
I'm saying for the first time,
Oh,
when
I
you enter from the left, the blue into the PDS, it's still one photon, right?
Yes, yeah, yeah,
Like this interferometer experiment where you have
yes,
exactly one thing happening, but there's a probability of.
yeah.
Why is the pulse there?
Pulsed, that's, I mean, the actual idea of getting a pulse laser, we just ordered 2 of these, so this is what we had available. But this crystal is designed for pulsed laser light. Most of our experiments use pulsed laser light. Very little bit, yeah, so as I was saying, our heralding efficiency, which is the efficiency that both processes basically happen, is quite low. It's 5%, and we believe it's due to some spatial mismatch happening, which shouldn't be the case because we have an interferometer, but it might be some very slight spatial mismatch happening, which then gets amplified by our collection optics. Coincidence rates through the network, we're only getting about 100 coincidence counts per second due to losses in the fiber network. This one is just the fidelities of our target, about the state we're creating relative to our target state. So it's not as high as we necessarily like. We still have some knobs we can turn. We haven't fully optimized this yet, but this is more or less good enough for whatever CHSH measurement we want to do on our network. And we see that it's stable over the course of this measurement. It was 20 hours. So this is, this I don't think I have time to actually go through in detail, but the idea of purity of our source, which is how much information you get from the spectrum of the source. We're supposed to have something which is very pure. We shouldn't, if we measure the wavelength of one photon, we shouldn't get too much information about the other photon. We don't see that good of a purity. We're looking into other setups as well as other crystals to improve this.
Why is the 3 centimeter long crystal? If the mode is a problem,
yeah,
it's easier to get a clean mode in a shorter crystal. Right?
Yes, it's easier, but then I don't believe we get this at least theoretical. This is theoretical, but I don't believe we should get this theoretical, very factorable source. So this, again, I didn't design the crystal myself. This was another graduate student in Paul's lab. They used the SPDC calc to figure out the parameters for the crystal to get a good factorability. Okay. So this is just in the lab. We took a CHSH measurement every 15 minutes for 36 hours to show the stability of our source. We see highs, 2.7s, all within basically error bars of each other. So stable over the course of these 36 hours. So we basically verified that our source was good enough for the experiments we wanted to do. And this is actually what we show the public is this, we want the public to choose this A and A prime measurement angle. So there are 4 measurements, A prime, B prime, and B. We let them choose A and A prime basically. And then from there, you see that the different CHSH values between A and A prime, you only start to see this entanglement verification after a certain setting. So we want the public to sort of explore these different bases sets and see that, oh, only sometimes we can prove that there's entanglement. And so this is data we use to allow people to see that CHSH if our system is down or under maintenance. So this is taken over the actual network, and we add to this as people come and use the network.
What is that topmost point? How much was it?
This should be, I don't know, it should be around 2.7 something. It seems a little above, but it shouldn't violate that 2.82. Yeah. The actual public part, I'll just very quickly go through this. When you enter the library, right to the right of that front desk, you'll see this table with superposition, entanglement, measurement, sort of 3 stages. The idea is people will come, they will see 3 polarizers. If they go through this guide, they'll see that there's some weird things happening with light and polarization. And that these polarizers actually change the state of the light once it passes through it. This is just very like a toy model of a SPDC crystal. This acrylic block is supposed to be a SPDC crystal, and then they see using these two polarizers, which are intertwined with each other using gears, that the intensity of it, both the beams, varies relative to each other, or with each other. And finally, they'll get to this measurement stage where what they'll have access to is this half-wave plate, which is attached to this sort of gear-looking thing. And with that, they can change the polarization of light coming out. They see its horizontal, vertical, diagonal, anti-diagonal components. We measure the power at each of those four and reconstruct the actual polarization state, which they see. And once they see that, they can then choose that A and A prime angle by moving this half-wave plate and then tell it to do the measurement. Yeah, so this was the first version. So this was actually when it launched, and you'll notice the people here. So these were actually graduate students talking to each other. That's what I meant by not automated. And I'll let you know where we are now, which is we don't need people to actually do the measurement. So this was the actual launch event, as I said before. So we actually showed that CHSH above 2.3 in front of this whole audience, which was like well over 200 people showed up to the first launch event. Right? Yeah.
I saw liquid nitrogen ice cream.
Yeah, this was for the kids,
Okay.
so that the kids came there, they had something to do.
I thought I read it wrong.
No, that's actually there. Because you see, there's like, we'd like to think this is the youngest user, but there might have been someone time back later who's even younger, but yeah, we had our mascot interact with it. And then, yeah, we had other like games and stuff for young children as well, quantum themed. And since we launched it, we've had over 300 interactions. People come to the library and do these measurements, though most of them have been drawn from that previous data it showed, because we were still getting this automated system to work and other maintenance tasks. But, and also, if any of you have young children, Professor Lorenz came up with this quantum network theme coloring book. You can find it if you scan that QR code. There's other, so Professor Kuyat actually runs a quantum theme lab, escape room at University of Illinois. So if you're ever there and want to do that, you can go here. And this is where we're at with the network as of now. So you see that the people have been replaced with these VPNs. So now when the user comes, tells the two measurement settings, there's some communication between computers, which actually carries out the experiment. So someone comes in, they basically get to the point where they have two measurement settings. It's a Raspberry Pi on the UFL side. The Raspberry Pi tells the computer in the lab, okay, do the measurement with these two basic settings. It communicates with the Raspberry Pi in the network closet of the library, tells it to go to some measurement angle. It keeps a measurement angle in the lab and carries out the set of measurements needed to do the CHSH with those two bases, calculates the CHSH, and sends that number back now to the user. And they'll see whether or not they violated the quality or not. And here, this is just, we corrected for the polarization once before we started taking this measurement. And then we see these 2.4. This was taken later. This data was taken like May to June. And May, early June, we see this 2.4. We basically violate the CHSH over the course of over 2 days. So we are at the point where we can go in and correct for it once every day or two and let the people actually use it the rest of the time. So what's next? The state of Illinois has given us fiber that connects us to Chicago. There's this center point, actually called Kankakee. They have a community college there. We're planning to work with them both for our experiments, which will run all the way up to Chicago, as well as creating a public quantum node in Kankakee. Fermi National Accelerator Lab, which is in the Chicagoland area, right around there. They have a visitor center. So all self-contained in the Fermi Lab campus, we're planning to have another public quantum network. as well as we're planning to open up in the future some node in Champaign to go along with the node in Urbana. By next spring, in time for Valentine's Day, we're planning to build some sort of thing using maybe something like QKD, building off of QKD to allow people to send each other quantum valentines using the public quantum network. And then by next summer, we're hoping to work with local high school teachers to introduce quantum curricula in K-12 classes. And with that, I'd like to thank all the people who made this project possible, and I can take further questions.
What's the benefit of that for this?
Good point. So, like, not quite. So very technically, yes, because you can because we're doing a PBS to do the measurement.
Oh,
There's like a caveat. But if this was just a polarizer here, right? If we lost this, basically what's happening is that the photon, because it's probabilistic, there are multiple photons, some of them actually get split. So if there was a actual polarizer here, we'd only get the photons going through, we'd lose the other information. So basically we're doing the measurement in the library and then the detection in the lab. Yeah.
Already a lot of answers during the